Hello, this lesson is not a skills-based lesson. This is a theoretical lesson. So remember the product rule and the quotient rule? Those are very useful rules. The product rule and quotient rule are things you could use even without knowing the proofs, but we still went through the proofs because seeing the justification behind these statements, it was illuminating. It was instructive. It made see how everything falls into place. So the following lesson, just like showing the proof of the product and quotient rules, showing the proof of the fundamental trigonometric limit, this is a lesson where you could just sit back, relax, and enjoy, because you will not be asked to replicate the proof of this statement. Well, what statement? First, let's recall the definition of a critical number. It's a number in the domain such that f prime of c is 0 or f prime of c does not exist. Why are critical numbers relevant? Because inside the collection of critical numbers are numbers c such that f of c is a local extremum. I used the adjective useful to these critical numbers. There are critical numbers which are useless. They would be those outside the broken circle and inside the collection, the set of critical numbers. But at least we know that if the function f has a relative extremum, it could only be at a critical number. No other number outside this solid circle will yield a relative extremum. So that limits the suspects that we have to investigate. That would lead us to a relative extrema. This is a fact that we've assumed for so long. I said before I was going to prove it. Well, now's the time for that. It's all based on this theorem. Alright? Well, the fact is that if you have a number c in the domain, then either f prime exists at c or f prime does not exist at c. But, well, that raises the question as a counterpoint to this theorem. Well, first let me read the theorem. If f has a local extremum at c and f is differentiable at c, then f prime of c is equal to 0. Okay, so again, f prime of c either does not exist or f prime of c does exist. But if f prime of c exists and f has a local extremum at c, why does f prime of c have to be 0? Why can't f prime of c be 7? Or why can't f prime of c be negative 10? So let's prove this theorem that if f has a local extremum at c and f is differentiable at c, then f prime of c has to be 0. Alright, let's prove this. Now, our premise here is that f has a local extremum at c. First case, suppose f has a local minimum at c. There's an illustration of a graph which has a local minimum at a highlighted point. Let's assume the x-coordinate of that point where the local minimum occurs is the number c. It doesn't mean, though, that this point is the lowest point in the entire graph. This is just a truncated portion of the graph. Who knows, maybe it extends further to this direction and that other direction that I'm pointing at. But it's possible to zoom in, truncate the graph, such that this point is the lowest. So therefore, there is an interval, a neighborhood, a fiefdom, a small kingdom, such that over this interval surrounding C, or you can even take it to be centered at C, then the point at C is indeed the lowest. So I've labeled for specificity this interval I as C minus delta and C plus delta. So it's just saying from C you go to the left and from C you go to the right, and those are the endpoints, such that f of x is greater or equal to f of c for all x in this interval. So all other function values in the neighborhood of c are greater than or equal to f of c. Let's consider two cases. First, um, two cases about the location of x in the interval I. So aside from x being c, x is either here on the left of c or x is on the right of c. Suppose x is on the right of c. X is between c and c plus delta, which are the assumptions in this if statement. Let's have a look at this difference quotient, which some of you might recognize as something that's going to figure in the derivative of the function f. Alright, because we're trying to prove f prime of c is equal to 0, so that means we're going to have to look at the limit definition of f prime of c. And that limit definition involves precisely this function, or at least one of the definitions of f prime of c. Well, in particular, what do we want to consider here? Let's consider the sign of this fraction. So that means we're going to have to investigate the sign of the numerator and the denominator. Now, for the numerator, recall that f of x is greater than or equal to f of c. So that means the numerator is, for convenience, I wrote plus, but of course it can be 0. Strictly speaking, I should have written greater than or equal to 0. On the other hand, what's the sign of the denominator x minus c, where x is greater than c? So it has to be positive. So therefore, what is the sign of this fraction? Greater than or equal to 0. This fraction is greater than or equal to 0 for all values of x on the right of c in this blue interval. So therefore, the implication is that the limit as x approaches c from the right of this difference quotient would have to be greater than or equal to 0 because, well, you're taking the limit of an expression which is non-negative, so therefore the limit would have to be non-negative. Now, on the other hand, what if x were to come from the red side, the left side of c? So x is between c minus delta and c. Let's see what the sign of this same difference quotient is going to be. Alright, f of x is still greater than or equal to f of c for all x in this interval I, whether x is coming from the red side or blue side. So that means the numerator would still be positive, or strictly speaking, greater than or equal to 0. What about the denominator? This time, x is lower than c. So therefore, the denominator x minus c is negative, making the fraction less than or equal to 0. Now, here's what we're going to do. We're going to take a similar limit, but recall that for this to be true, we had to assume that x was less than c. So therefore, we have the following conclusion. The limit as x approaches c from the left of the same difference quotient is less than or equal to 0. Now, where exactly are we going to use the assumption that f is differentiable at c? Well, now's the time for that. F prime of c exists. Therefore, the limit definition of f prime of c exists, which means the limit as x approaches c from the left and as x approaches c from the right are equal. But from our blue and red conclusions, this limit, that's the blue limit above, it's greater than or equal to 0. And the second limit, that's the limit above, red limit, is less than or equal to 0. Because f prime of c exists, f prime of c is equal to both of these things, and therefore it takes on any attribute that these two things have. So therefore f prime of c is simultaneously greater than or equal to 0, and also less than or equal to 0. The only way that would happen is if that number, f prime of c, is 0. And voila, that is what we are trying to prove. Again, though, don't forget, we were assuming that f has a local minimum at c, so we're operating under case number 1. Case number two, suppose f has a local maximum at c. I'm going to leave it up to you to figure out how the proof is going to be modified. It's going to be a similar play on the signs of certain expressions, but if you're lost, you might want to refer to the book, because the book actually shows you the proof for the case where f has a local maximum at c. And because that's readily available, I decided to do the proof for when f has a local minimum at c. In case you don't have the book, just ask, if not me, your classmates, or, well, you have the proof here, try to figure out where the modifications would have to be done. Bye-bye.